Okay, I'm going to have a chat about domains and ranges. Does anyone have any specific, say, exam questions that bother them about domains and ranges? Or something like that? Did you have anything in mind? Whoever said that? I can't remember who said that. Right, well, let me start. Unless otherwise specified, the domain is the most x's the set of the most x's which make the function defined. So domain or if it's not a function of x, it'll be t's or whatever it is. Okay? So I'll do an example in a second, but the quickest way to define a domain is to find the places where it's not defined and remove them and remove them. Okay, so the quickest way to find a domain is to actually find the places where it's not defined, and the domain is everything except that. Okay, so sometimes you're given a domain, you are told x has to be in this zone, in which case that's the domain. If you're not told what it is, you have to just find all the x's that actually make it defined. The range is the set of values that come out of f of x. So thinking of your function as a machine which takes inputs called x and spits out answers, the set of values that come out of f of x is the range. So they're quite different, okay? The domain is defined, they're both defined by the formula, but in different ways. Okay. The hardest things to do domain and range of is composite functions, where you do like f of g. So I'll get to that eventually, and I'll make sure I do one of those. So the easiest way to talk this through is to talk about it as examples, but I'm going to have an attempt to give a generalized idea. So finding the domain of an ordinary function is, I would say, first find all values where it's not defined, and to make a set out of everything except that. All x's except that. Okay, so this will make sense when I do an example. Okay, so the key things that you are looking for when you're looking for domains are, in fact, I'm just going to come back to that example. I'm sorry. You'll see that when I do a revision seminar off the top of my head, sometimes I think of good answers afterwards. The key things to look for, 1 over x is undefined for x equals 0, and so therefore only defined when x isn't 0. Root x is undefined for x negative. Ln x is undefined, so it's undefined for x negative and defined for x greater than or equal to 0. I'm just going to put them both in. It's undefined for x less than or equal to 0 and defined for x positive. Okay? They're the 3 classic things to look for. Pretty much everything else isn't going to come up. Okay? So now I'll do my example. So the first layer, I'm going to work my way out from the outside to the inside. This will be undefined when whatever is on the bottom is equal to 0. Okay? So undefined when ln x equals 0, which means it's undefined when x is 1, because that's when ln x is 0. Okay, that's my first step. And my first pass at trying to find out where it's undefined. It's undefined when ln x is 0, which means it's undefined when x is 1. Okay? But it's also only defined when ln x is defined. Okay? It's only defined when ln x is defined, and then ln x is only defined when x is positive. So my exact answer back there is wrong. I'm going to not find all the places where it's not defined. I'll find a combination of where it's defined or defined based on my classic things I look for. So all the x's where it's defined, except where it's not. Okay, I know that sounds so like a grandmaism. My grandma used to say all sorts of things like, your father would be a taller man if he had longer legs. Yes, I suppose. Yes. All the x's where it's defined except the places where it's not defined. Right. Yeah, but you'll get what I mean here. Okay, so it's defined only when x is greater than 0, but not when x is 1. Okay? So let me just draw a picture of all the x's for which that is true. There's 0. It's only defined where x is greater than 0, and it's not defined when x is 1. So that's an open circle there. Okay, so my domain of f is everything from 0 to 1, not including either 0 or 1, and everything from 1 to infinity. That's interval notation. I could also have written it as that's the most natural way to write it though. I could also have written, or the domain of f is everything from 0 to infinity without the number 1. But that's not nearly as pretty as that one. Let me do that one. So it's undefined when e to the x plus 1 is negative, which would mean e to the x would have to be less than minus 1, which is impossible, right? Not possible. So it's always defines. So therefore, the domain of f is all the real numbers. Which, if you really want to write it in interval notation, or the domain of f is from minus infinity to infinity. But either one is fine.
So that would be a straight line.
Sorry?
What would that be?
That's the whole of the... It's all of it. Well, remember, we're only... Oh, I didn't even draw it on the screen. We're not drawing the function, we're just drawing the parts of the x-axis that we're allowed to use. So the domain is always a piece of the x-axis. This one I'm only allowed to use this piece of the x-axis. This one I'm allowed to use the whole x-axis. It is a straight line, but the function itself is some wicked curve. I don't know what it looks like. So remember that the domain isn't part of the function. The domain is the places on the x-axis where you're allowed to do the function. So yeah, it's sort of if you draw a light, put a light above your function and draw a shadow downwards, it's the part of the x-axis that's in shadow. So wherever my function is, it's sort of up here somewhere. All of the x-axis is in shadow because I've used all of it. Does that make sense? Okay. I could come up with these off, yeah. So just a final one. I'll just do this round the other way. That one there. So e to the anything is always defined. I don't have to worry about that. Undefined when whatever's under the root sign is negative, which means it's undefined when x is less than minus 1. Alternatively, you could say it's only defined when x plus 1 is positive or 0. So we're going to end up with it's defined when x is greater than or equal to minus 1. Okay, so therefore the domain of f is everything from minus 1 up to infinity, because it starts at minus 1 and you're allowed to have minus 1, so it's a closed bracket. I should point out that in completely technical sense, a domain is a set, so it must be written as a set. Okay, you're not allowed to write it as x is greater than or equal to minus 1. You have to write it as a set. Interval notation or proper sets, or the real numbers. So just one final one. You would say it's undefined when x plus 3 is 0, which means x is minus 3. So therefore, the domain of f is everything except minus 3. So that's one way of writing it. You could also imagine it as a line, everything but not minus 3. So you could also say the domain of f is everything from minus infinity up to minus 3 and everything from 3 to infinity. Either of those would be acceptable. I should point out that if they say interval notation, you must write this one. That's domains.
So wait, if the bottom one is called interval notation, what's the top one?
It's just set notation.
Oh.
General set notation, right? That's the real numbers is the name of a set. The without symbol is something you can do with sets.
Nothing minus 3. Right.
Thank you. Yes, because if it started at 3, there'd be a big gap in the middle. Yeah, which is a possibility as well. So, all right, that's domains. The only other thing, technically, we have actually dealt perfectly well with the domain of composite functions here. All of the functions that I've just written are composite functions. This is the result of putting x plus 3 into 1 over x. This one is the result of putting e to the x plus 1 into root x. So if you want the domain, yes?
Could you show us how the domain affects the inverse function?
How does the domain affect the inverse?
Yeah. Like, can you show us how it affects the inverse? Like when you take the inverse and now you have to use the domain, like the range.
Yep, okay. I can only do that after I do the range, of course. So I'll do the range first. But remind me if I forget. Yep. Yep. This one? 1 over e, which is still positive. Yep.
In an exam, if like, suppose you had to find like the derivative of something and then it said and hence find the range and domain. If you got the answer wrong in the first place, but then you got the range right for the function which you found it for, would you still get the marks for it?
Yep. So the question is, if you had to differentiate something and then they asked for the derivative, what's the domain and range? Yeah. If you got your answer wrong and you worked from that point forward, they will mark it right based on where you came from. Because they know how stressful an exam is. So, they're not that mean. Unless the whole thing's only worth 1 mark, which it wouldn't be, but yeah. They're not allowed to give half marks for anything, they have to only give whole number marks. So if you have enough stuff and it's only a little bit wrong, then they'll likely just give you the whole mark. So just weren't pointing that out. Okay, so finding ranges. Finding ranges is hard. Okay, it's not easy. What you have to do is you have to try and find all of the values that come out of your function based on putting all the values in that you're allowed to put in. And it's not easy, okay? You're trying to think forward to all the things that could happen. It's the same as the domain in terms of the graph. On the graph, the domain is the shadow that it makes on the x-axis. The range is the shadow that it makes on the y-axis. Neither of them actually live in the function itself. They live on the axes. I actually don't like to think of it in terms of the function. I actually think of it in terms of just a list of all the numbers that come out, because that's the easiest way for me. And when I find ranges, what I normally do is I ask myself these questions. Can it be 0? Can it be positive? Can it be negative? Does it have a maximum? And does it have a minimum? Okay? They're my questions. And you don't write them all, you don't write it down that way, but that's what you ask yourself. So I might try and use the same functions I had before. So my first question, can it be 0? And the answer is, well, no. The only way it could possibly be 0 is if x was 0, and it's not defined when x is 0, so it can't be 0. Okay? I'm going to draw my y-axis and start marking off things that it can be. So it can't be 0. Can it be positive? Yes. I could stick in some positive numbers and it'll be positive. Can it be negative? Well, x squared is always positive. But ln x can be negative if x is less than 1. So ln of a half is negative. So yes, it can be negative. Okay, that's a good start. Can it be, so it can be both positive and negative, so that's good. It does have some here and some here. Does it have a maximum that it could possibly be? Ln x is always less than x squared, like quite a bit less. Ln x is always less than x as well, actually. So I reckon, since the top is bigger than the bottom for all possible x, I reckon it can be as big as I like. Okay, that's my start. All right, so it can go as big as I want. Is there a minimum it can get down to? Well, what was it? There was a problem spot at 1, wasn't there? There was an issue at 1. It wasn't defined here, was it? So if ln x is 1, and if x is 1, ln x is 0, dividing by 0 gives me infinity, so I have a feeling it's shooting up there. If x is positive but really close to 1, it'll be just the answer will be close to 1. This one's really hard, as I've said. If x is negative, if x is less than 1, I do know it's going to shoot down to negative infinity. It's going to go to 0 at this point. I reckon it does have a minimum, but I'm not sure. This one's too hard and I wouldn't put it in the exam. At this point I would graph it and see what it does. So this is too hard. Okay, point that out. Yeah, the lnx on the bottom is just crap. It can be positive, it can be negative. I do have a feeling that it has a minimum. The only way to be sure would be to try and differentiate it, but that's going to cause all sorts of pain. So that's too hard for the exam, we're just going to leave it. Yep.
Could you find the inverse and then get to the minimum?
You could, but do you think that it would be fun to find the inverse of that? Yeah. But that is a useful approach. Damn. Should have picked better examples, but I was making it up on the spot. That function there. There is another approach. Think of what the graph looks like and use the graph. This function here, I'll ask myself again, can it be 0? Yes, it can. If x is 0, it's perfectly possible for that to be 0. It's great. So it can be 0. Can it be positive? Sure, if x is a big number, it'll be positive. Can it be negative? Yep. If x is a negative number, actually, that's okay. You know, if x is like a really small number, like a half, it'll be negative. So yes, it can be negative. Does it have a maximum? Okay. Well, I suppose. Yeah. If x was like 1.0001, I'd be getting like 1-ish divided by a tiny number, so it'd be shockingly huge. Cool, so it can go up as far as I like. It can go down as far as I like, I reckon, by the same reasoning. So is there something that I can't achieve?
X is equal to 1.
Oh, I can't make x equal 1? You're right. I can't make x equals 1. So that's my final thing. Is there anything missing? I can't make x equals 1. Because for x to be equal to 1, I'd need x to be equal to x minus 1, which means 0 would have to be minus 1. That's not going to work. So therefore, that's the only thing I can't make. And I'll just check that by trying to draw this function. There's another way of making this work. X minus 1 is x minus 1 plus 1. X minus 1 divided by x minus 1 is 1. 1 divided by x minus 1 is that. That function, it's much more obvious that I can't make x equals 1. The only way to make x equals 1 would be for this to be 0, and it's impossible for that to be 0 without x being infinity, so I can't make x equals 1. But I should be able to make any other function at all. And just for the graph, well, 1 over x would look like this. X minus 1 would shift it up 1, and the plus 1 here would shift it up 1 on the y-axis, so it's going to be like here. So in my graph, if I draw a shadow, put a light over here, my shadow is going to miss that spot there because there's no y value there. So my range is everything. So my range of f is the whole of the real numbers without 1. Okay. One final one that's actually easier. So can I make 0? Well, no. In fact, the smallest that could possibly be is 1. Because e to the x can go all the way down to, but it can't be 0. So that's my thinking behind it. I'm just going to run through this thought process. e to the x is greater than or equal to 0. It can't actually be 0, it's strictly greater than 0. So e to the x plus 1 has to be greater than 1. So root e to the x plus 1 has to be greater than root 1, which is 1. So it has to be more than 1. It can't be 1, because there's no x that will make e to the x equal to 0. And presumably if I make x big enough, I can make it as big as I want. Okay, so therefore my range of f is everything more than 1 but not including 1. As I've told you, it's not at all obvious how to do ranges. It is hard. If you have a good instinct for how graphs should look, it helps, or a calculator that can help you do that, but sometimes you have to zoom out or in to see what's really going on. If a function has an asymptote, a vertical one, your calculator will sometimes do strange things near that if your view window's wrong, so just be careful with that if you're graphing things. Ranges are hard. They try and give you ones that it should be fairly obvious, like that one there. And you asked me about ranges and domains of inverses. Let's do that function there. What about f inverse? Well, you've got two ways of going. If you've already found the domain and range of your original function, you just switch them up. Okay, so I had the domain of f was the whole of the real line. The range of f was from 1 to infinity. So therefore, the domain of f inverse must be the range of f, and the range of f inverse must be the domain of f. And just switch them up. If you haven't already found the range, and you are expected to find the domain of the inverse, the quickest way is to find the inverse and then look at it. So as an example with this one, or find the inverse. So I always find an inverse like this. I go y equals the inverse on x, and then I do f of y on both sides x. But f of y would be subbing y into the formula, so it's root e to the y plus 1. And now I solve it to get y equals. Do ln on both sides to get rid of the e. And that's my formula for the inverse. Oh yes, thank you. Okay. That makes more sense. So I could, if I wanted to, if I didn't want to find the range manually by just staring at it, I could find and especially if I was being asked to find the inverse in the first place, I could just find the domain of the inverse, right? So this is defined when x squared minus 1 is strictly positive, so x squared is strictly positive, strictly greater than 1. Interesting. And so mod x is greater than 1. When you square root something, when there's an inequality sign, do it as a mod x. So this would mean that minus 1 is less than or equal to, x is between minus 1 and 1. No, greater than. Mod x is greater than 1. If you think about what mod x looks like, it's greater than 1 on both of these sides. That's giving me x is greater than 1 or x is less than minus 1. That's not the range I found earlier. I actually know that this is wrong, so you do have to just go back and check if any of those are actually disallowed by your original function. Let's go back to the original function. It's positive square root, so only the positive answers are actually valid. So, comparing outcome of f of x can only be positive, so therefore x has to be greater than 1 for this domain. So therefore the domain of f inverse is from 1 to infinity. That's an important thing you're going to have to check, because when you do the squared, it introduces other numbers that actually satisfy it. So what actually happened here is this was all great. This is defined when x squared minus 1 is positive, blah, blah, blah. Mod x is greater than 1. It's actually technically possible. If x was like minus 2, mod of minus 2 would be more than 1. It can't be both of these. I just have to check. Remember that these x's are the y's from the old function to see if I compare these to the outcomes of f of x, I can go back and say, well, f of x can only be positive because it was a positive square root. So therefore, my x has to, f of y, if you like. That makes more sense. Back here, f of y here can only be positive, so x is a positive square root. That makes more sense. Comparing the outcomes of f of y can only be positive, so x has to be greater than 1. So I get this. And so therefore, just to flesh it out, I've got that the domain of f was the whole of the real numbers. The domain of f inverse was 1 infinity. So that means that the range of f would have to be 1 infinity, and the domain, the range of f inverse would have to be R, because they switch over. I should have written them lined up, I'm sorry. If I was thinking clearly. So if you do have to find the domain and range of the inverse anyway, it is quicker to try and find the domain, but do be careful. If it's got a square root in it, you'll have to chop off some of the answers. I think I just made it more confusing, I'm sorry. Right. Yeah, I might skip composite functions. The quickest way of dealing with composite functions is to just write what the whole function is. But do be really careful. There is an exception to that. Just one more example. F of x is x squared. G of x is root x. H of x is g of, no, I want f of g, sorry. F of g of x, and we want the domain of h. Okay, if you do this, h of x equals f of g of x, which is what the little circle means, which means f of root x, which means root x squared, which would be x. If you did that, you'd look at your formula and go, well, that's defined for all x. And the answer is that would be wrong. That is not the domain of h, because h is not x, h is f of g. Think of it like a computer. If you've told the computer that in order to calculate h, first you have to do g, and then you'd have to do f, and you tell it, right, find h of minus 2, it'll go, I have to do g, cool, root minus 2, error, okay? So it's not going to work, and that's how we have to think about it. We have to say, in order to do f, in order to do h, first g has to be defined. So, to do h, g must be defined first. So that means that root x has to be defined. So in fact, x has to be greater than or equal to 0. And then, in order to do f on g, f has to be defined at the places that g is defined, at the places where the answers from g come out. But that's okay, x squared is always defined. So then...
Does that mean you have to find the intersection?
Not quite. You have to find... I'll draw a picture of it in a sec. Just give me 1 second. Then f has to be defined, but x squared is always defined. So therefore, we've still got x is greater than or equal to 0. So the domain of h is x is greater than or equal to 0. Now I was just asked, does that mean you have to find the intersection? Well, sort of. Not quite. If you imagine it like this, suppose you've got, these are your x's, and instead of drawing it as a graph, x goes to y, I'm just going to draw the y-axis that gets produced. I'm just going to draw the range. So, okay, so each number here produces a number on this thing here. So if it was root x, if I put 5 in, I get root 5. I put 25 in, I get 5, and so on, okay? All right, and so these are the answers from g of x. And then those answers are subbed into f of x. So I get f of g of x. So imagine that that's the domain of g, for example. And imagine that this is the range of g. Okay? So this is the domain of g. That's so bad. And this is the range of g. Okay. Then, let's think about f. F is taking these numbers and producing new numbers. So what if the domain of f was here? Like that. And maybe the range of f is here. In order to do f of g, I have to do this and then this. Oh, sorry. I have to do this. I have to pick a number x here, do g, and then do f. That means that my answer from this x has to fall into this zone here. If it comes out of g, it has to be here, but if it goes into f, it has to be here. And so I'm intersecting the domain of f and the range of g. But I'm not even really doing that. I have to actually work my way back and say, just a second, if I used this bit, then that would end up in this zone. And so that's the domain. You have the domain of f of g is the part of the domain of g which produces answers such that the answers are in the domain of f. Yay! But you don't normally have to think about that at all. You just go, well, let's look at the inside. And I've done it so many times. You just go, just a second. I look at the inside. That's my inside function. Whatever that is has to be positive, and that's always true. Yay. Or I look at this one. I have to look at my inside function. Whatever the x plus 1 is, it has to be positive. Cool. That would require x to be greater than minus 1. Okay, so I've had to restrict the x's that are allowed so that when I put them into x plus 1, the answers from that, those have to be positive. But you don't have to worry about any of that because you just look at the annoying bit, which is the root or the ln, and say the entire of that has to be positive, solve that equation, that tells you what the x's are. So, but if you're asked to think about it in a general sense, that's what's going on. And it will also change the range too, because if I only use this part of the domain, I might only use like that part of the range. So, yes. to be honest, in the exam, you'll do what I did. Yes?
I think I've come across a question before and it was like, write the domain is the intersection of two other domains or something like that. And
Okay, I know when that if one is.
yeah.
That's when you have a function like this. Something like that, which would be done as, or it would have been written as, you know, g of x is 1 over x and h of x is root x plus 3 and f is g plus h, something like that. That's an alternative way of saying the same thing. So, in order for f to be defined, both 1 over x and x plus 3 have to be defined separately. So g has to be defined and h has to be defined, and it won't work unless they're both defined simultaneously. So you get the domain for g and the domain for h, and you have to find the places where they're both satisfied, which is an intersection. So that would be the idea behind it. The domain of g is everything except 0. The domain of h would be from minus 3 up. If x is less than minus 3, I'll get a negative under the root sign. And I can draw those two. So there's minus 3, there's 0. This is the domain of g. This is the domain of h. And you could say the domain of f is the domain of g intersection the domain of h, which is r without 0 intersection minus 3 infinity. But if we just look at our graph, the part that's in both is that bit, but not the 0. So it's minus 3 infinity except 0. That's one way of writing it if you want. Or you could just as easily write it's from minus 3 to 0 and from 0 to infinity. And often they'll say write it as the union of two intervals, which is what that is. All right. I've missed my train already, so I might call it a day. Thank you very much. Drop-in Centre is still open tomorrow. Video for this will go up soon enough. And don't forget all the other revision seminars. Thank you. Good luck with your exam.